Yeah, so we continue with the tour of selected classifiers, which we call part 3. So recall that in the past few weeks, the 2 weeks, we started talking about the concept of selecting brief, very common classifier that are being often used in classification or regression problems. So we take us quickly to what we did last time. So last time we discussed the KNN, which is a very popular classifier. Very simple. We discussed how it works. So how to choose the value of K. And then we give example, then the pros and the cons. So today we're going to majorly continue with the description of KNN, and especially we're going to demonstrate from using Weka package, how you can run your first machine learning experiment using Weka for a very small data or very interesting data. We're going to be using chronic kidney disease data as an example. So before then, let's brush through. So we discussed last time that in developing k-nearest neighbor, the very common, very important thing is the number of K. See, the number of K you want to use is very important. So this is going down way to really determine what's likely going to be the value we can get. So, and I compared k-nearest neighbor to a very simple aphorism that people often say that, show me your friend, I will tell you the kind of person you are. So the person you are closer to is likely going to be a kind of a reciprocal of who you are. So that is the principle of k-nearest neighbors. So when we want to classify if somebody is having a chronic kidney disease, we have set of patients. So we have some attributes. So we calculate the distance between this person, we don't know his own category. We compare it with the other one that we know very well. And then we see who is closer to this particular person. So if we choose our K to be 5, for example, so that if it's closer to 3 and these 3 are having chronic kidney disease, and the other 2 that are also closer, they are non-chronic disease. So because of majority voting, so we are going to classify such sample to be chronic disease patient. So and that is why the value of K is very important, and we describe how you choose the value of K. We also describe another very important hyperparameter, which is the similarity measure. So we talk about the Euclidean distance, the Manhattan, the Minkowski, that these are very important different type of distance function we can use. And when we are dealing with, we often use these ones for distances that are numeric. You see, numerical attributes. Sorry, for numerical attributes, we use this for them. So our attribute is having numbers, so we are going to use this to calculate distance. However, if the attribute is categorical, for example, you are asking the gender of the patient. So we see male or female. So in that case, you are going to use something like Hamming distance to compute the distance between them, and then we take decision who is faster, who is farther away, or who is closer. And we also we had a look at something like this. So whereby this is the sample, we don't know where it belongs. So k-nearest neighbor is one of the lazy classifiers. If you remember, we categorize classifier majorly into 2 groups. We have the lazy learner and the eager learner. So in the lazy learner, it just keep whatever training set you provide for k-nearest neighbor, it keeps it in the memory. So there's really no model building. It keeps that training set in memory, and you know the training set, we know the output of the training set. So when you have a new sample like this that is unknown, so we try to find the distance between that unknown sample and every training set that you know their classes. So which one is closer to this sample? We found out that this is the guy. So we are using K to be equal to 1 here. So we are going to assign this unknown sample to class A. See? So in the same way, we decide to say, okay, who is closer to, depending on the number of, here we might say, okay, our K is equal to 3. So in that case, you can see that it's 1, 2, 3. These are the 3 closest samples to this unknown sample. We don't know the class of this sample. So, but when you look at, we want to take our K to be equal to 3, Then we now check out and see that, okay, there are 2 from class B that are closest to this, and only 1 from class A that is also as close as this, the other 2. So from class A, we count it, it has 1. From class B, it has what? 2. So majority cast the vote, so this is majority voting. We are going to assign this one to class B. So this is simply how it works. So that's why this is the generalized step for it. You calculate the distance, you find the closest neighbors, and then you vote for the labels. Very simple. Now, so the algorithm is often given as such, as explained last time. You choose a K. So choosing the value of K, we gave a couple of advices also last time. So for every new instance you want to calculate, you want to determine or predict the class it belongs, you have to find the K closest training point with respect to the distance measure. So the distance measure also can be changed under the parameter optimization to see which distance measure is going to work for this problem. Because the principle always holds, let the data speak. Always remember this principle. So we don't know the number of K that is going to be optimum for your problem. It could be 1, it could be 3, it could be 5, it could be 7 or 9. If you are dealing with binary classes or binary classification problem. See? So to know the class where the new sample belongs, so you take a majority vote among the K points. So this is a very simple way of how K-nearest neighbor algorithm works. And as simple as it looks, usually it's very accurate in some cases based on experience. So, and sometimes it may not work. But generally, if the data is not huge, K-nearest neighbor, the size of data is manageable, it could be a very good thing to take note of. However, once the data size is very large, then it becomes very challenging. Now, so to determine the value of K, we pass through what we call the parameter tuning. So you don't really know, okay, which parameter, which K value is better, although people give a lot of examples. So, but we have to actually, I believe so much in that principle of let the data speak. You have to search for the parameter that is the best for you during the training process, during the building of the model process. Now, we also explain to ourselves, you have to take notes. If you are solving 2 class problems, you make sure that you have odd value of K. See? And generally, the general advice is K must not be a multiple of the number of classes. So if I have 2 classes, I cannot choose my K to be 2 because there's going to be a problem in my voting. Since this class can have 1, this one has 1, then I'm going to have a problem who is going to be the class to be assigned. So that is a very, very important rule to note. So if I have three classes, then it means you have to make sure that you don't choose multiple of number of classes. Otherwise, you have problem during the voting process if they have a tie. This is usually why this rule is very, very important. We all take note of it. It's a general rule. Now, so the main challenge of K-nearest neighbor is the complexity in searching the nearest neighbor for each example. That's the main challenge. Every time you have a new sample to be classified, because it doesn't build any model. You see, unlike the Higa learner, as we are going to see them later, inshallah, this one doesn't build any specific model. So whenever you have a new sample, it has to compute the distance between this new sample and all the training sets. Imagine you have 1,000 training sets. It has to do that. Then to arrange it in ascending order or descending order, as the case may be, to select the closest, that is those with the least distance to this new sample. Maybe I'm using 11 nearest neighbor. So you select the first 11 that are closest to this new sample, and then to take a voting. In these 11 samples, how many of them belongs to class 1? How many of them belongs to class 2? So the majority will be the class to be assigned to this new sample. So imagine if the number of samples we have in the training set are very, very sizable or very huge, then K-nearest neighbor might run into trouble. So then we gave example last time, and I remember also I gave us example to try from home to try to practicalize how it works. See it? Very simple, interesting example. You are given this kind of data. This is the training set, and they say anybody who score 4 in maths and then 3 in CS fail. You can see pass. So you try to find the distance between them. We want to use k-nearest neighbor to solve this problem, so that if we are given new sample, you can see this new sample wasn't part of the training set before. So we want to classify, is it pass or fail? So k-nearest neighbor said, okay, calculate the distance. So you decide to use Euclidean distance here now. What is the distance between this and this new sample? That's what we are doing. The distance is this. Distance between this and this new sample is 1. So you calculate the distance between each of the samples that you know their classes and the one you don't know. So we now say, okay, where are the closest one? If we are using K to be 3, K is equal to 3. So we want to select the closest 3 samples. You can see this is 1, 1, 2. These are the 3 that are closest. If you look at them, some people will decide to rank them. You can arrange them in ascending order. You can see the one that are closest easily in case the data is huge. So you have 1, 1. This is the distance, and then 2. 3 point something is higher. 5.3 is higher. We have 1, 2, 3. So you now pick these 3, and then you see which class do they belong to. This is 1, 2. Coincidentally, the 3 of them belong to pass. Fail, no, 0. 0 count. So therefore, we are going to assign pass to this particular new sample that we don't know. See, this is how k-nearest neighbor works. And we can see intuitively, you can see somebody score 6, score 8, then definitely it's going to pass. So this is just an example. So when we did give this and ask us to try it, you can solve it using your k to be equal to 1, k is equal to 3, k is equal to 5, to try to see how it's going to actually work out. So as I said, we are going to demonstrate here an example of how this kind of system can be used to solve a problem. Now, with that one, you can apply the example to any problem manually just to see how actually it works. So you are given these samples, so you have to calculate the distance between these and this one that we don't know the class it belongs to, either it is normal or underweight, normal or underweight. So you check the distances, then you can use your voting using case 1 or case 3 or k is equal to 5 because it is a binary problem, binary classification problem. But if you have more than 2 classes, then you have to select your k in such a way that k is not equal to multiple of the number of classes. I think that was where someone will ask us to try to solve the problem from home. Now, during the question time, if we face any issue there, we can definitely ask and then we can discuss further, inshallah. Now, what are the pros or the advantages of k-nearest neighbor? One of the major disadvantages of a k-nearest neighbor is that it is very simple to implement, very, very simple to implement. And also KNN execute quickly for small training data set. If your data set is very small, it can quickly solve the problem. And the fact that it's very simple to implement is usually a quick point of call when you have a data set to model. And one of the principles of machine learning is to keep it simple. Start from something simple before you go to something complicated. So anybody can easily understand how k-nearest neighbor works. Unlike when we go further to the eager learners, see some of them are really dependent on very complicated mathematical formulations, optimization procedures, quadratic equations, depending on the kind of model we're talking about. But for KNN and the family of lazy classifiers, they're often very simple and straightforward. So one of the advantages is the simplicity of implementation. So, and also you don't need the prior knowledge about the structure of the data in the training side before you use it. You just go ahead with the procedure. No training is required. So if the training pattern is added to the existing training set, this is another advantage of k-nearest neighbor. You see, if you build a model using other modeling technique, other classifier we call eager learner, since already they learn from that data and they built a model, if you increase the size of your data set, you need to build another model again. That is for the other eager learners, for the eager learner. But for lazy learner like KNN, there's nothing like that. So if you increase the size of your training set, you added more, you don't need to do anything. You just continue to use it as you were using it before you even added it. Because since you don't really build any model ab initio. So these are considered the advantages of or the pros of k-nearest neighbor. As for the cons, the disadvantages include that when the training set is large, it takes a lot of space. This is one, space problem, because the training set needs to be stored in the memory whenever you want to calculate the distances. So if the data is really huge, that could be a very big disadvantage in that respect. Then for every test data, the distance should be computed between test data and all the training sets. Therefore, a lot of time complexity will be needed for the testing. So since when you have a new sample, every time you have a new sample, you have to compute the distance between it and every training samples. So imagine you have several testing cases you want to check. So look at how many times you're going to repeat the distance measure. So this is where computational complexity comes in. And once the data set is huge, for sure, KNN is not a good option in that respect. Apart from it's going to take a lot of space, your system will run out of memory for it. At the same time, you need time, a lot of time to do the computation, especially if the number of samples that you want to predict, you want to test to check the value, to check the classes they belong are many, then you're going to spend a lot of time computing the distances repeatedly. Now, so these are the pros and cons on k-nearest neighbor. Now, if Dr. Rashid is now available, now you can ask your question. I think we lost you at that point in time.
Yeah, I'm very sorry. I think I lost connection. Yeah, okay. My question has to do with the example you gave with respect to finding the k-nearest neighbor.
Okay.
And where we have 3 points, I will appreciate if the slide can be shown. Where we have 3 points something, and you said it's higher, hence it shouldn't be considered. Thereafter, you have to consider 1 and 2.
Yeah.
Our K is 3, right?
Yeah.
And we have 3.1, and we didn't consider it. I think 3.1 might be closer in my own distance because than 2. I don't know why we should we not consider higher number when we are looking for the.
No, when we say okay, thank you very much for that. Let me clarify that. Thank you for that. Well, when you say nearest neighbor, we are looking for nearest neighbor. Nearest means the closest person to this sample we don't know. After doing the calculation, we got the distance between this sample and this new one is 1. Another one is 1. Another one is 2. Somebody is like, let's say meter. It could be a meter or kilometer. Somebody is 1 meter from me, 1 meter from me, 2 meters from me. So I'm looking for 3. I'm looking for 3 neighbors that are closest. For sure, this is 3 meters. This guy is far away from me. This is 5 meters.
Okay.
This guy is far away from me. So I'm not going to select them. This is why we have to select the closest guy. We are not looking for the highest value. See, it's the opposite actually. When you say nearest neighbor means the person with the shortest distance to my house. So this one is having 1 meter from my house, 1 meter from my house, 2 meters from my house. That's why I selected this guy, and then this guy. So I'll now look at which class, since we are using 3 neighbors, so it's going to be 3. Then we now calculate them. This one belongs to class 1, pass. This one is also pass. We said that this one is also pass. So we want to vote. The 3 of them all are in the same class. So for sure, I'm going to categorize this to be courtesies. If I decide to use 5 nearest neighbor, then in that case, everything will be considered because since I'm using 5, so it's going to be 1, 1, 2, 3.1, 5.3. Then I'm going to use what are the classes? 3 of them will be pass. Then 2 of them will become fail. Still, pass is going to have majority, so I will still assign it to pass as the classification. I hope that is clear.
Yes, sir.
Okay. Barakallahu. Now, so thank you for that. So let that clarify also for others. Tips. We say KNN perform better with lower number of features than many features. Usually when you have lower number of features, KNN could perform better. These are just tips, actually. It depends on the data set. So research has shown that in large dimensional Euclidean distance is not useful anymore. These are a couple of experiences from people that large dimension means once the number of features are many, Euclidean distance may not really work anymore. You have to think of other distance measure. Of course, like I used to tell us, always know that let the data speak. So try to check out what are the distance measure that will work for me, irrespective of the number of features. Now, therefore, you can prefer other measures such as cosine similarity, which get decided less affected by high dimension. So based on experience, some cosine-based similarity are less affected by high dimension. But then again, it depends on the data set. Yeah. So in short, we can say that KNN could be a good option for you if your data set is relatively small. Of course, small is a relative term. Somebody might want to ask me how much is small. Let the data speak. Use your data. By the time you start running it and it's taking too much time, you know that KNN is not an option for you because it's going to take too much time. And then the memory also is going to take memory because it's putting everything in memory. Unlike some classification algorithm, for example, support vector machine, inshallah, we're going to discuss later. When you train support vector machine, it will select something we call support vector. From a very big data, it will use very few support vector to represent them. See, you see the advantage of that later when we discuss it. But for KNN, all the training set will be put in the memory. So, of course, use KNN when your data is labeled. That's why it is supervised learning. So when you don't have label for your training set, it might not be an option at that level. And also data is noise-free. That is, your data is closer, it's closest to the ideal data. Your data is not dirty because data could be dirty. If your data is dirty, for sure, it's going to affect the distance you are going to be calculating to the new samples, and it's going to affect your final decision that you're going to be making as the case may be. Now, I think this is how we're going to have it then, theoretically. Now we're going to move to the demonstration now. We want to demonstrate for us to see how can we use this k-nearest neighbor to solve a problem from the medical field as an example. I have a data set here for you. Actually, this data set is about chronic kidney disease. You see, you can see we have two classes. This patient is actually diagnosed of having chronic disease. This one is non-chronic disease. This one is non-chronic disease, chronic disease. We have, sparingly several of them, chronic, non-chronic. You can see them now. And they will have just only three features. Of course, there are many features. I think feature selection cleaning has been done to the data set. So this is like I think this is the blood urine and the urine nitrogen. Why this is creatinine, and then this is the red blood cell. These are just the three features being used in this case. So now we're going to open our friend Weka to see what we can do with this data. So of course, as usual, you open your Explorer. See, you open the Explorer. So once you open the Explorer, the first thing is in the Explorer is for you to open the file. You can see everything is gray out. This is Weka now. You cannot do classification, you cannot do clustering, you cannot use the other functionality. So the only thing you can do first is to open your data. You can open data from the local file here. You can open the data from, if the data is located in the website, you can just open the URL to open the data. You can also open database if the data is inside one special database, or you want to generate your data. You can also generate your own artificial data. These are the options you can use. So we go to our data since we have our file. And mind you, so I already converted that file. It's not in ordinary Excel. You have to save it as CSV file. So there's one of our earlier video, you can check it on, that talk about how to load your data from Excel. Because originally data for Weka are loaded through text files that are formatted in a special way. But formatting it in a special way can be challenging for people. So you store it in Excel, save it as CSV, and then you can load it into Excel. If you like, you can save it later in the format that we can actually use, which is the text format. Now, so we open the data. Okay, I think I put in my documents. There's something I call Weka experiment. Okay. See, you can see KNN, you can see the data, you have to pay attention to that. So because the file I want to open is saying ARFF data file. This is the file originally for Weka. So I have to say open CSV or all data file. See, CSV data. This is what I want. So this is what my data is here. So that in case you want to open your data, you can locate it. It means that you have not selected the right type of file here. So you have to check it to make your CSV. Now, this is my data. So I'm going to open the data. Now, the data is open. Okay. So now we have, you can visualize each of them. This is the first feature. See, these are the values. This is the minimum, the maximum, the mean, the standard deviation for those data is shown. The second feature, the creatinine value, you have the minimum also. Then you have the RBC, the red blood count. So it has the minimum, maximum, mean, and standard deviation. Now, this is the class. You can see the class. Here you can see chronic kidney disease and non-chronic kidney disease. So this one, these are 126 people without the disease, while there are 118 people with the disease. So it's not balanced, but it's closer together. This is okay. The difference between the positive class and the negative class are not much. That's fine. Now, so having successfully loaded your data, now the next is, and usually when you arrange your data in the Excel, it's better, the class should be in the right mode part of your Excel file. So once you put in the right mode part, Weka will automatically load it as the last one here. And that's why it call it class. See, it call it class. Yeah. Even though in my own system, it's call it class or whatever name you assign to it. But if you don't put it at the last column, then in that case, it might assign it anywhere near, but you have to manually designate it as this is the class I want to predict. For example, if I decide to want to use another one to predict, I have to change it and specifically tell that this is the one I want to predict. Now, so now the next thing is this, the data is ready now. You go for classification now. See, go inside and choose your classifier. We are working on that lazy classifier, remember? So we are working on IBK. In Weka, IBK is the k-nearest neighbor implementation. You see? So IBK is selected. Now, you have selected the k-nearest neighbor now, which is called IBK in Weka. Now, the next is to run the experiment. But before then, you need to specify how you want to build your data, how you want to partition your data. The default is cross-validation, 10-fold cross-validation. I think we explained this a lot before in our previous videos. But let us, to make it simple, easier for us, let's use percentage split, holdout method. So we want to use 70% or let's say 80% for training. The remaining 20% is going to be for testing. Now, so the system, we divide the data into two. It will keep the 80% as the training set for this k-nearest neighbor classification task now. So the next is to start. You click start here. You're going to run your first experiment now in Weka using k-nearest neighbor. Yeah. Start. You can see it's done because the data is not much. So it finished quickly. So what has it done? It has calculated the distances, compare them. So the result you are seeing here, it is the result of the 20%. I've mentioned it before. The 20% that is used for testing, this is the one you are seeing the result here. If you want to, this is the result of those 20%. So you can see out of these are the correctly classified instances 45 correctly classify 4 mistakes, which the classification correctness is 91.8%, while this one is 8%, the error. This is the confusion matrix, the one we use to explain. This is confusion matrix, where we have the false positive, the false negative. We are not going to that for now. At least let's see the way it works. Now, once you run the experiment, based on some of the previous questions that have been asked by our members here, we want to see if you want to check the number of K, because presently now you can see K nearest neighbor here. You can see K is equal to 1. If you look at this place, you can see my mouse hovering this portion. You see, these are the most important features. We call them hyperparameters. Yeah, the hyperparameters for the classifier. They are usually mentioned here. K is equal to 1. You can see K is equal to 1. And also the distance measure is Euclidean distance. Euclidean distance. So if I want to change it from K to 1 to K is equal to 1 to K is equal to 3, I have to click this place. So I'm going to click this. You can see now. You can see there are so many parameters, but the hyperparameter is, there are only 2 here. KNN, the number of K, nearest neighbor, and also the kind of search, the distance measure you want to use. See, these are the options. You can see here, Manhattan distance, Minkowski distance, Euclidean distance. Shape distance measure is also there. Now, let's start from optimizing our K. K is default, which is 1. And now you can see what we got here. We got 91.8. So you keep it with you. Then I change the K to be 3 because it's only 2 classes. There are 2 classes here. So class, which is chronic disease or non-chronic disease. Yeah. So when K is equal to 3, let's see what we are going to get. Change it to 3. Okay. Now you run the experiment. You can see. Take note that the error moved down from 4 to 3. And then you can see the accuracy increased to 93%. Then I go back again. So it seems there's an improvement. Let my K become 5. So usually what I recommend is, as you are doing it, put your result in an Excel file. 91. Now you have 93 point something. Keep putting it there, and then you can plot a curve that will show the result going up as you increase the number of number of K. The value will be going up until the value start coming down. At that point, it start coming down, then you might stop, because that means this is the optimal, the best you can get for that particular data. You may bring another data set. It might be K is equal to 1 that is going to be the best for you. We have seen that before. Sometimes it could be K is equal to 3. It could be K is equal to 7, sometimes 11. So it depends on the problem, and that's why we often say that let the data speak. Now I change my K to be 5. I run the experiment. You can see it has moved to 95. The error goes down to 2. I have 95% accuracy. See? So I can keep going up and up like this. Let's say because of time, let me choose 11. What I'm going to get for 11. Now I choose my K to be equal to 11 now. Let's see. You can see now it goes still going up, 97. So it means you can keep trying up. Now the error now is only 1. Maybe it's going to get 100%. Who knows? So maybe I go to 13 and see how far it's going to perform. Can you notice something now? It has gone down to 95. You see, 11 gave us only 1 error. 13 K nearest neighbor has reduced the performance down to 95 from 97 point something. This shows that I might have to stop at 13. So it means my optimal K for this data set could be 13. This is one optimization. I've only worked on the K, and you can make a plot to indicate what you have done. Linear search, so we want to change with what we have done now, we have been able to see that with K is equal to 11, we got the best result for this data. We tried to go to 13, the result came down. So that could be a place for you to keep it a stop. Then if you like, then the next hyperparameter there is to play with the Euclidean distance. See, You go in here and then try to change the distance measure. All along, it has been using Euclidean distance. Why don't you use shape distance? Maybe it's going to get you a better result. Sometimes some distance measure might have problem with your data. You see, no, nothing changes now. So you go back again and then try with another distance measure. Choose another distance measure, Manhattan. Maybe it's going to improve it. Okay. You can see, yeah. So you can see that when I change the distance measure, even with 13, which was not good for the previous one, it became better now. It reduces the error. So these are the two most important hyperparameter we have in K-nearest neighbor. And the most important of them is the K. That's why usually you first of all check for the K. When you get the best value of K, then go ahead and change it and see maybe they can map up with a better result with your distance measure. So now, so this is 97. This is the maximum it could get also, even with the change in the distance measure. So this is how you use K-nearest neighbor in Weka practically from the practical point of view to classify if somebody is having a chronic kidney disease or not. So, and I think one more thing is to measure is, like I said, these are the results, and then this is the confusion matrix that has been produced at a particular point in time. So once you check for the best K, you check for the best distance measure to be used, then you are done on your experiment, and then you can be able to go ahead and compare your result with others. And then if you like, you can also use cross-validation. Usually if the data is not much, cross-validation is encouraged. We have discussed this in our previous sections. So why do we use cross-validation? Usually when the data is very few, you have very few samples, you go for that. And sometimes you want to divide data to 3. Someone asked me this question. Let me clarify this. You see, Weka has no way of dividing your data into 3 automatically for you. So, but if you have to divide data into 3, you have to do it first manually. Let's say I have like 3,000 data sets. I want to use 500 for validation. I keep that one as number 3. I'll remove it from my file, from my Excel file. I keep it somewhere in one file. Now, so now it means I want to divide data into 3. I've already divided it manually by keeping 500 samples as my final testing set later. Then I bring the remaining ones now, which is now 2005, into the system. Then I'll now specify percentage split. Look at 2,500. How much do you want to be training and testing? So you specify the percentage now of this data. So once you build the model, you're going to see the result of the testing directly. Now, for you to supply the one you kept secret, you didn't put it to the system, the third part partition, you have to come here and say supply test set. Because your model is built already. You have a model already built. Say supply test set. You now go in and upload that file, the 500 sample you kept away from Weka. You now upload it from wherever location you put it. Then once you load it, now you now click run. You click start. It will use the model you already built to do what? To validate. It will validate that model using that particular supply test set. So this is the way that we want to divide your data into 3. So one of them has to come in later manually. While the first training and testing, Weka can do that for you. Some people also actually, they don't want Weka to divide their data for them. Sometimes the company will send you data. In some competition, they'll send you the training set separately. Then they'll give you the testing set separately in different Excel file. In that case, you cannot ask Weka to divide it because they gave you training set separately. So what you do, you use this option. You say use training set. You select this option, use training set, which is the set you already you are going to put it in. You're already in the pre-process set step. This is the one you open here. So the one you have selected here is considered to be the training set. So you say use training set that I've uploaded. That is the data uploaded now should be considered as training set. All the samples. There's nothing like dividing them. Then you click start, it will train. Then you now say supply test set. You now go back to the file that contains the test set, then you upload it again, and then you can click start, and then it will run the testing for that particular data. I decided to clarify this because sometimes in some competitions, they give you separated training sets, another testing set separately. So in that case, you don't need Weka to divide the data for you. The data is already divided by the client or the supplier of the data. So this is just a few clarification regarding how you load data. And like I said, we already had a video on how you can load data through Excel to your Weka in our archive. So try to check it out. And then if there's any other clarification later in the question time, we can clarify. So I think this is what we're going to have today for the KNN neighbor. If there's any question, then we can have a couple of questions before the end of the class. Thank you all for listening, and I wish you all the best.